shut the lights off for this first part.
Yeah.
And what I would like to do is share some slides with you guys, just to give you a little bit of background about the lumbar motion monitor. Well, how many of you have actually used this before? And one of you has used the old lumbar motion monitor.
Tried to.
You tried to?
Yeah.
Okay. Yeah, so I'll certainly show you. This is going to make your life a bit easier and show you the new one with the new software. So this is kind of our agenda here. Just give you a quick introduction, the uses of this industrial lumbar motion monitor, some of the research behind the development of this device, as well as the risk model that you can use, that the inputs go into, the design of it, and we'll talk about the components, and then we'll get into a couple of details about the Ballet software. That's the software package that comes with this. And then what I would like to do is actually just do a workshop. So I'll get a guinea pig. One of you guys can volunteer to put this thing on, and we'll kind of just walk through it together, if that's cool with you guys. Sound good?
Yeah.
Still pumped up?
Yeah.
By the way, I'm Jeff Hoyle. I think I introduced myself to everybody that came in. With the Ergonomics Center of North Carolina, which, for those of you who don't know, we are actually part of your department, part of the Industrial and Systems Engineering Department. We are currently located just off campus behind the Applebee's and the Burger King, but primarily what we do is ergonomics consulting for companies nationwide, as well as internationally. Now we're doing some work down in Honduras and Dominican Republic and Puerto Rico. But we do also get into some applied research every now and then, and actually partner with you guys, partner with faculty members and students to help us conduct the research. So if we have a client that's interested in getting into this level of sophistication, rather than just using, general observation-based risk assessment tools, we can, leverage you guys and your expertise in some of this technology to get into more deeper dive analysis. Okay. That makes sense? Just kind of a high-level overview of us. So we'll start with the introduction, the uses of the industrial lumbar motion monitor. I'm sure everybody's read all of Bill Maris's research articles, right? That part of your curriculum? No? Yeah, well, he's more on the physical. I think several of you guys are on the cognitive side. But when it comes to low back risk assessment and low back injuries and ergonomics, he's pretty much the man. So he was actually one of the gentlemen that patented this device. So you can see it's made up of, this is the new one, by the way. You have a waist harness, and we'll get into this when we get into the workshop. Strap it around here, and then you have a shoulder harness attaches like you see there, and then you just have this little connection here. Basically, it's just a power connection. And what this actually does is it tracks the amount of forward bending, flexion and extension, the amount of lateral bending, as well as the amount of twist. And since it's capturing that, obviously, over time, it calculates velocities and accelerations. Okay. For those of you who have seen the old one, and maybe we'll break it out during the workshop, you'll see this is much more compact, portable, and it's not a huge exoskeleton of the spine like the old one is. And this is actually wireless. It's telemetry. The old one, you had any worker that you're analyzing, you had a long cord connecting to them, and you had to keep up with the cord. Now you can do that with the new one, but you have the option of using telemetry, wireless. So the applications of this lumbar motion monitor, mostly for industrial use. So it does have a risk model, and we'll get into the risk model and the development and what the outputs are for that risk model a little bit. And then it also can give you specific trunk motion data. Like I said, it'll track how much flexion and extension, how much lateral bending, as well as twist. So you can get those movement patterns and output that data as well. Okay. And I should say this is really geared more around lifting, okay? At least with the LBD risk model. It's really for two-handed lifting, analysis of that task. Okay. But as far as trunk motions, I mean, you could really, whatever they're doing, you can still track the trunk kinematics. You just can't input it into the LBD risk model. This will make more sense when I get into more of the details. Good to go? Still with me? Boring you to death yet?
No.
With the lights off? I know it's Thursday, right? Okay. So again, any kind of, just throw in a few examples here, any type of specific trunk motions that you want to assess, you can use this device. As long as you don't have any, obstructions or constrained environments. I probably wouldn't recommend this for like mining work, where they're inside of a mine on their knees. So if you don't have any obstructions, in the back, you can again still use this device to track trunk kinematics. Okay. You could use this even for clinical use if you're trying to see differences in range of motion between users or ranges of motion, before an intervention and after an intervention to see if they're improving. Since again, it's giving you kinematic movements of the spine, you could use it for clinical use too. Just wanted to throw that out there. Does that make sense? Again, this is pretty informal, guys, so if you have questions, please feel free to stop me, all right? So the research leading into the development of this, we're good with the first bullet? Basics? No questions? This really helps us determine how much is too much, okay, in terms of lifting and the risk associated with lifting. So it gives you a quantifiable output. The idea was to quantify the workplace and trunk motion factors that are associated with manual handling and how that's associated with low back disorder risk, LBD risk. Okay. So when they developed this thing, they basically went out, and you'll see they looked at over 400 different industrial jobs and collected over 100 different data points per job, and basically threw everything into this analysis model and tried to pull out what is predicting risk. Because they looked at the injury data for all of these 400 plus jobs and tried to figure out what is really driving the injuries. Okay, what workplace factors and what trunk motion factors impact risk. Okay. So why this level of evaluation and analysis? You guys have talked about Nash lift equation. Everybody's been exposed to that, right? At the 81 and the 91. Yes? Yep. Most of you. Have you guys been exposed to 3D SSPP? It's a biomechanical static modeling software. Okay. This is a software that basically allows you to position a person into a posture assumed, apply the forces at the hands, both the magnitude of the force and the direction of the force, and then it'll calculate moments about different joints, and then compare those moments to strength capability values and tell you what percentage of your population is physically capable of performing that particular exertion. And then it'll also calculate some static compressive forces on the spine at L5, S1, which is, as you guys know, bottommost disc in the spine, and one up from that, L4, L5. But it's a static model, right? So it does not include motion. Which obviously, as you guys know, force equals what? Mass times acceleration. So if you're looking at a static model, well, if we're not including motion, that's half of the darn equation, right? So this is really one of the only dynamic risk models for low back. Okay. As far as NIOSH, which you guys are familiar with, the 81 had low sensitivity, high specificity, and I'll talk a little bit more about what that means, which you guys probably already know. And then the NIOSH lift equation was highly sensitive, but not very specific, and we'll talk about that. And we've mentioned that last one there. So most tools out there are static. There's no motion built into the wrist, and this is really one of the only ones that does. By the way, this was developed out of the Ohio State University. You got to put the D in there, right? Sounds more premier. By the way, I did my grad program at the Ohio State. I did my undergrad here, okay? So I'm still a wolf pack at heart, okay? And I guess, did anybody know Gary Merka? He used to be here as a faculty member. He also co-patented this lumbar motion monitor. He used to be a faculty member here at NC State. He's now at Iowa State, I believe. So as far as the NIOSH lifting guide, the 81, I mentioned it was high specificity but low sensitivity. So, if you looked at low back disorder injury rates via OSHA 200 logs, which are just the tracking logs for injuries for companies, if you had a job and the lift index score was more than 3, which means it's a high, it's a hazard, right? It only really predicted 10% of those. Okay, so it wasn't very sensitive. Now, if it was a low-risk job, the lift index was less than 1, predicted that pretty well, 91% if you got that right. Okay, but really we want high sensitivity and high specificity, right? Does that make sense? Am I confusing? We're good?
Makes sense.
Okay, sorry. Yeah, you guys are probably all smarter than me anyway, so hopefully I'm not trying to talk down to you or anything. So the 91 equation was highly sensitive, so if it showed up as a hazard, 73% had predicted that accurately. However, if it was a low-risk job, well, I guess we'll look down here. It actually said that it was a high risk when really, if you look at the injury data, 23% of it, there were no injuries. Okay. So it really didn't do a great job in predicting that. And I've mentioned this and emphasized it, I think, enough. It does include motion. So as I talked about before, this actually is tracking how much forward bending in the sagittal plane, how much side bending, frontal plane, and then how much twist in the transverse plane. Three-dimensional space over time calculates velocities and accelerations. And as you guys know, which we talked about, force equals mass times acceleration. So in terms of compressive loading or shear loading on the spine, which is what drives injury, again, this is really one of the only tools that does that. So just a quick, kind of a quick picture here. This is the 3D motion. You have sagittal, lateral, and this is twist. Those 3 axes of a low injury rate job. Okay. So when they looked at those 400 plus jobs and looked at what the motion aspects are for those jobs that didn't have any injuries, that's what it looked like. Now compare that with a high injury rate job. You can obviously see the difference, right? So what do you think? Do you think motion makes an impact on injury? Yes. So again, once they measured these things, threw it into some of these statistical models, and then pulled out what is really driving injury the most. Obviously, they looked at range of motion differences, and really saw, in terms of just flexion and extension, lateral bending and the twist. Not looking at velocities and accelerations yet. Just looking at the degree of difference. The only one that was really statistically significant was sagittal. Okay. So you'll see when we get to the risk model, one of the parameters that goes into this risk model, there's 5 of them total, is maximum sagittal flexion. Okay. And this is why. When they compared high injury to low injury jobs. Okay. Then they also looked at velocities, which again, degrees per second. And it was significant with all 3, sagittal, lateral, as well as twist. So you will see in your risk model that there is a component for lateral velocity as well as twist velocity. Okay. That's 2 more of the 5 parameters. I mentioned this already, 400 plus jobs over 50 different industry types. Don't worry about the grade ones out. This was just how the slide was kind of put together just to distinguish between every other little cognitive ergonomics, even though gray on white is probably not the best scheme. But you can see a variety of different industries, and again, looking at material handling applications, lifting, specifically for the lumbar motion monitor, LBD risk model. Good? Boring you to death? Okay. And as I said, they looked at over 100 different measures, kind of a shotgun approach, measured everything out there from distance the object was from the employee, which you will see as part of the risk model. Obviously object weight, and that's part of the risk model. It's a function of both of these together. Load moment is basically what it is. Start and finish heights, lifting frequency. They look at anthropometric data of all the subjects that they ran. Looked at injury history, looked at even job satisfaction, so they did some psychosocial data collection, and then obviously took the motion parameters with the lumbar motion monitor. Okay. Then they basically broke it up into low rate jobs and high rate jobs. So low rate was considered, there were no low back disorder incidents basically over 100 employees over a year. That's essentially what 200,000 man hours is. Okay. So that was their category for low rate, and then high rate was 12 or more low back disorder incidents over 100 employees working for a year.
I have a question for the last slide.
Please.
What exactly classifies an incident? Is it an
These were,
incident,
I guess, these were
a
actually
loss?
recordable incidents. So
Defined by OSHA.
yes, defined by the OSHA 200 or OSHA 300 logs.
Okay.
So it had to show up under one of those tracking logs for it to be considered an incident.
Okay.
So if it was like a first aid or something that, you could just be treated internally or something, it wasn't captured here.
Okay.
I have one other question
Yeah,
related
good
to this.
question.
How did
Yes.
they decide the threshold there? The 12 incidents threshold?
I don't know, to be honest with you. I don't know. I mean, that's basically 12 out of 100 employees. And what this will make more sense when we get into the output, but this basically gives you the percentage, the probability of that job falling into the high risk rating. Okay? So, and we'll talk about the different thresholds for green, yellow, and red.
I think like the 200, how we got the 200,000 hours that we,
That's kind of standard for incident rates
yeah, per year, I think.
per year.
50 days per times 8 hours times the number of
Times 100.
employees, right?
Yeah.
So that means that at least once a month instance.
I see. Yeah, so you're trying to explain it, the 12. Yeah, I mean, maybe that was it. I wasn't part of the initial developers of this, but that's a great question, and certainly I'll give you the references if you, there may be more of that detail in those references. I can't answer it, to be honest with you.
That's fine. That's
In this
fine.
case, we do not consider the types of the instance.
It's just low back injuries only was what they're trying to predict the risk of here with this model.
Okay, according to OSHA definition, like zero instances and low severity of accident,
It didn't matter about severity. If it showed up on the log, then it was considered an
only
incident.
recordable.
If it was a recordable, yes. Yes. Okay. Good to move on. So again, once they took this shotgun approach, threw everything into a statistical model and tried to pull out what was most associated with those high and low injury jobs, and what they came out with was these five things. Okay, you have lift frequency, maximum moment, And you'll see this lift frequency is actually how many lifts total across any given shift, okay, one day. Maximum moment, which is a function of how much weight you're holding and the distance essentially from the spine that you're holding. Okay? So those two inputs make up maximum moment. And you'll see with the software you have to input this information. Maximum sagittal flexion, which I told you how much forward bending that they're doing. And that's collected with the lumbar motion monitor. You don't have to do anything, it's tracked there. Average twist velocity and maximum lateral velocity. Okay. Those 5 things predicted risk the most. Good?
Is there any specific, sorry, for
It's
the
okay.
last slide, is there any specific reason why they didn't pick the maximum twisting velocity instead they just took an average twisting velocity?
It didn't flag as highly significant when they put it in the statistical model as what this one did. It's just a function of the data. That's what the data said. So they let the data tell us the story. So again, why this level? Again, the limitations with the other assessment tools includes motion, and it really is more predictive than some other assessments, including NIOSH. If you look at the odds ratio comparisons between what this said and injury data, you can see that the lumbar motion monitor risk assessment was what? More than 3 times more predictive than both the NIOSH 81 and 91. Okay. But obviously the counterpart is, this is an added level of sophistication, time to collect the data is a bit more intrusive, measuring, strapping this onto somebody and taking those specific measurements. So I'm not saying that you'll never use these again, because I use them on a day-to-day basis with my job. But you can convince, if you're doing consulting and you can convince them to go into this level of analysis, it can certainly be worthwhile, and you can see why. Okay? Good? I didn't take my 5-hour energy this morning, so at least I'm not over the top here, okay? All right? And it also allows one to look at trade-offs. An example. This is the output for the LBD risk model. Just one example, it's a truck assembly, a door hanging job. So they're lifting a door. You can see the 5 outputs, and these are all essentially weighted. And how these scales are set is they're equally weighted across in terms of, this one basically gives you a percentage, this gives you a percentage, and so on and so forth. You can see what the percentages are there, and then it basically takes an average of those 5 and gives you a final score. So this one looks like it's what, about 65 or something? So what's driving the risk the most in this example?
The moment?
The moment is, yes. So if we're focusing on one thing that we want to maybe change about this job, first I would start with the moment, right? Which is a function of what?
Load that's being carried by the employee and also the distance about which he's going to pick.
Exactly right. The weight and the distance away from the body. Okay. In this example. The second worst one is twist velocity, right? Average twist velocity. So if there's a way, maybe we can stage things so that they don't have to twist. Everything's more in line. Maybe they're going from here to here, placing the door. So you can kind of play those what-if games with this to figure out how can we improve this job. Okay. Really, the sagittal flexion is really not driving up the risk, so there's not a whole, if we implement a lift table or something to get it off the floor, well, to start with, we don't have that much maximum sagittal flexion, so probably not going to make much difference. Okay. Make sense? Okay. Here's another example with a small panel inspection that they're having to lift, what's driving the risk in this point? In this example, I guess.
Lift rate and also.
Lift rate and the twist, yes.
I have a question here. Like, does the limitations of the NIOSH equation, like the employee, if he moves from his work cell, you cannot use your NIOSH equation. So, does the limitations of lifting equation apply to this risk model that we are using?
You're talking about in terms of like a carry?
Yeah. Like.
I would break it up into two separate. This really doesn't give you, an assessment of the carry because it's not a lift.
Mm-hmm.
So if you have a lift from point A to point B and then you have a carry, and then another lower or another lift from this point to down here, I would break those up into two different tasks. And you can analyze those two tasks independently. But then the carry, there are other assessment tools you can use to analyze a carry, like the Liberty Mutual Material Handling Guidelines, the SNOOP tables. Have you guys familiarized with the SNOOP tables, Liberty Mutual tools?
I just checked the Liberty Mutual tools just pretty.
I mean, you could at least get the trunk kinematic motions of a carry, but it's more than likely it's not gonna, it's not gonna flag really here, because you're not gonna really have too much. Because you may have a little bit of twist, but you're not really gonna have any sagittal flexion, and you're not gonna have any lateral velocity. You'd still have that moment, but again, this is really more for lift assessments. So you could still certainly keep the device on there, and my recommendation would be for that example, break up that first lift and then stop collecting the data, and then you can start back with that second lift. And I'll show you how you can break that up. You're still monitoring that data all along, it's just how much do we want to save. You can save a chunk here and a chunk there without everything in between. You can specify that with the software. Did I answer your question? And this tool is validated, which you guys have probably seen a lot of the tools out there that really don't have a whole lot of validation behind them. So they did compare the risk model to injury rates for these jobs that they looked at. So you can kind of see, and these are sort of the thresholds that are used. If we go back two. If you're 30 or less, the general rule of thumb is it falls into kind of a low risk category. If you're 30 to 60, it's in the moderate risk category. If you're above 60, it's considered high risk in terms of helping you prioritize. So looking at, this is what the risk assessment said versus, my laser pointers are kind of dying on me here, what the injuries were. So they looked at the three different job categories, high, moderate, and low, and did a before and an after. So what did the risk assessment say after they made some changes, and how did that correlate with injury rates? And I'm not sure, to be honest with you, the time frame that they looked at those injury rates, but I believe it was at least 3 years that they did the before, made some interventions, showed the decrease in risk from before and after, and then looked at the long-term injury rates for those same jobs. So you can see, obviously, we start here. This is the high. Didn't really change it much. And if you look at it over here, it doesn't really change the injury rates. Changes it some, but not significantly. And the same with changing it from high, again, above that 60% threshold, down to below 30%. And this is where you can see, it falls well under that 3 injuries per 100 full-time employees. Good? And this is all, I'm sure you guys have read these references, right? You'll print them off right after we get out of class and make sure you can take them home, read them. It is certainly worth, if you're interested in this and you want to follow up and answer maybe some of these more detailed questions that I can't answer, I would start there. Okay. And by the way, I will give you guys these slides
Yeah.
as well as an electronic version of the user's manual. Okay. So if you want to post that on the website or whatever,
Yeah.
feel free. Okay. So just getting into the design of this, again, the old ones, you had to have like we had two different sizes, a large and a small, for different sizes of individuals. The new one, you don't have to worry about that. It accommodates basically 90% of the population. So between the 5th and the 95th percentiles. So if you have like a person that's 6'5" or something, you may get, I mean, you can try to use it, but more than likely you're going to get some bad data. The same with the other end of the spectrum. So you get to using this on somebody that's less than 5 foot. You can try to use it, but more than likely you're going to get some not so great data. Okay. Again, it is telemetry, so you don't have to use a cord or wire, even though you do have that option if you need to. Right now it's on rechargeable AA batteries. It does come with a charger. You have 2 sets of batteries in here, so you have a backup. And really, you shouldn't even have to change these things out, but I mean, even collecting data, I believe they told me that they collected data for like 3 days straight and still didn't have to charge the same, the one battery pack. But just to be on the safe side, collect your data during the day, make sure you recharge the batteries at night. I mean, and again, you have 2 sets, so you do have a backup. Okay. And you do have that hardwired data cable if for some reason the telemetry isn't working properly. Some other improvements, they color-coded the waist and the shoulder harnesses just to make, the red connects to the red, the green connects to the green, so on and so forth. Leg straps are crucial. You do have to tighten the leg straps. It makes it a little uncomfortable trying to reach around the subject and basically putting these things right here, but you gotta do it. Okay. And then there's the software is that Ballet 2.4, which I'll show you. Some other peripheral components to consider if you're actually going out and collecting the data to input into this. Need a tape measure to collect what? Possibly.
Measured
Distance.
from
Yeah, the horizontal distance away from L5S1 or the spine. Extension cord, may need an extension cord or a power strip. And then data collection forms to help you do a task analysis and break it down and see which specific lifts you want to analyze. Right. And this is sort of what that, this is what that software actually looks like, and I'll pull this up and we'll kind of just walk through this together during our workshop. But it has a space for you to enter company name, job name, and then within that job you can actually break it down into different tasks. Okay. And then you can take multiple trials. This actually, it kind of flags you if you take less than 3 trials for any one task, a little window comes up and says, well, you can still run the analysis, but it recommends at least 3 trials, which again, I would recommend as well, minimum. So you kind of have that database structure, and then within each task, you put a little description in there, what the vertical height at the beginning of the lift is, what the vertical height is at the end of the lift, the moment arm at the beginning, which is again that distance, the moment arm at the end, the weight, the coupling, asymmetry, which, what is this? Looks familiar, doesn't it?
Those are all the modifiers of the lifting equation.
It's the Nash lift equation, exactly right. But this risk model uses the moment arm information that you input with the analysis. But there is a way that you can actually run the Nash lift equation through this software. But I'll go ahead and be upfront with you and tell you right now, the Nash lift equation running through this is pretty buggy. Doesn't work that well. It also has some of the Liberty Mutual stuff built into it, the psychophysical for carrying, pushing, pulling. but it's also buggy for that. A lot of times you can input all the information and then it closes down the software altogether. So right now, I wouldn't recommend using it for NIOSH or for that psychophysical Liberty Mutual. Use it just for the risk model. I will provide that feedback back to the software developers, so once we get the next generation, we'll have those updates. As far as calibration, it does allow you to do that, which I'll show you. This is the screen, comes up. Once we plug everything in, have it working, have the screen that comes up, and really we want everything to be at 0. Now for this, you actually keep the lumbar motion monitor in the case and have it staged vertically. Okay. And again, we'll walk through this one. But if you see, that this is kind of squiggly or outside of that 0, you can just hit adjust and it'll 0 everything. Okay, so it's an electronic calibration. This is the motion data that you can actually look at. So it's tracking lateral, sagittal, as well as twist. And you can see this on the screen when you're collecting data. And then you have basically your kind of your hotkeys, your function keys, to break it up into different tasks. Okay. So if you hit F1, it'll start collecting for that task 1. Hit it again, it'll stop collecting it. Let's say the next task was different. You hit F2 to start the beginning of that lift. Hit it at the end. Or if you're doing 3 trials of that first task, you'd hit F1 to start, F1 to stop it, whatever they're doing in between, F1 again to start, F1 to stop it. Okay. This is the motion data that you can output when you go to the data view screen. It shows position, velocity, and acceleration, and you can actually pick up to 5 different tasks and to look at at one time. And then you can select which ones you want to turn on and turn off. Okay. So right now it's just showing 3 different tasks for the position over time, velocity over time, and acceleration over time. And I will show you, there is a way to export all of the data. This is actually captured at 60 Hertz. So for every second of data, it's giving you 60 data points. And this is what that LVD risk model screen looks like. So it tells you that the overall probability of the low back disorder risk, 67%. So again, which category would that fall under based on what we talked about?
High risk.
The high, yeah, if it's more than 60, it's in the high.
I have a quick question on that percentage. Is that just a pure averaging of the 5 factors?
It's a pure averaging of the 5.
So they all showed a similar statistical significance in terms
Well,
of the...
that's why they've
impact, or-
scaled them the way that they've scaled them, is so
Okay,
that
so
they
they've
would all
included
be
the-
equally
Okay.
averaged.
Perfect.
Yeah, good question. So I believe maximum moment actually impacted risk, I think, the most of any one of them by itself. But the way that they've scaled them is
Okay.
such
So they
that
scaled the
they're
axis so they
equally
can just-
distributed, yes.
Perfect.
So yes, when you look at these numbers here, 8%, 82%, it's an average of all 5 of those to make up your overall probability score. Yes. And you can print it directly to a printer. A lot of times I'll just take a screen capture and then throw it into a Word document or a PowerPoint document.
I have a question.
Yes.
In this case, as you know, the 3DSSP gives this same risk value for a certain percentile of the population. Okay. So then this one is that, okay, in the moment, for example, probability is the X% for this type of job for the worker, right? So we do not consider,
These percentages are not based on what percentage of our population is capable, like your 3D model is. No. These percentages are the percent,
for this type of job, right?
the percent of likelihood that it's going to result in a low back disorder type of injury for each parameter separately.
that means then if the other person performs the same type of task, which get a different risk value. Is it true?
Well, you could, based on if they have different motion characteristics or they're lifting it further away from their body, you could see an increase in maximum moment. So you can certainly see differences between subjects. Typically, this is used, to analyze a job before and after. But if you guys wanted to use it to analyze differences between people, because maybe one person's using a good work method, so they're maybe not twisting, so they're actually moving their feet when they're lifting instead of twisting of the spine, which would be a good thing from a risk standpoint, right, for the back. You could actually show differences in one person versus another person and how that impacts your risk score based on somebody using good work methods or good technique versus another person that does not. Does that answer your question?
Yeah. I'm just trying to understand.
Same thing with maximum sagittal flexion. So, somebody might be actually lifting with using their legs and not bending down all the way. Then you may have another person that's going to be bending down like this and not using their legs. That's going to show up under which one? Maximum sagittal flexion, right? Okay. And like I said, you can export either a summary or all of the motion data that's captured over the runtime. Again, that's at 60 hertz into an Excel document, and I'll show you how to do that. However, one thing I actually noticed, we've just received this, so we haven't had this very long. I was running some tests the other day, and it only exports in metric units. So like for your moment, it outputs that in like Newton meters. So you have to do some conversion. I just wanted to kind of throw that out there. Another thing that I wanted to point out, to change the moment arm at the lift origin and the lift destination, you must change the input under the runs category, all right, not the task category, because it's actually pulling data from the runs category, and this will make more sense when I pull it up and show you live, but just keep that in the back of your mind. Okay. And I pretty much said this already, the Nice lift equation and the psychophysical functions built within this software don't function properly. So we can do the workshop now and cut the lights back on.